Ladies and gentlemen, my name is Tomas Doktor. I'm from Czech Technical University in Prague. Currently I'm working on the University of Maribor at Faculty of Mechanical Engineering during my sabbatical leave. And I would like to briefly introduce my contribution entitled Effect of Polymeric Fillers on Poisson's Function of Additively Manufactured Auxetics. Utilization of solid structures belongs to the modern bio-inspired technique when people try to mimic nature when creating engineering structures and mechanisms. The applications of cellular materials consist for decades in insulation, in extension of aeroactic surface, and some structural applications in biomedical engineering for implants and scaffolds for tissue engineering. But in my work I am focusing on impact energy absorption capabilities which are also provided by cellular materials. In last decades, among cellular materials, metal foams are of high importance in manufacturing of deformation elements like protective helmets or deformation zones or bumpers. When the cellular materials are of higher performance, they can be used also in some military application where higher impact velocities, higher strain rates occur, and higher portions of the impact energy are to be mitigated. The advantage of cellular materials consists in broader selection possibilities of such a material according to the impact scenarios and the intended protected application. The current effort in utilization of cellular materials consists in enhancement of impact energy absorption in such cellular materials when cellular structure can have controlled properties and can form a regular lattice, for instance auxetics, which this work is focused on. This direction was enabled due to extensive development of additive manufacturing techniques. Another direction how to enhance the impact energy absorption properties is use of filling materials which form together with the cellular structure so-called interpenetrating phase composite. The other possible directions are, for instance, coating of the open cellular structure which brings enhanced performance, or composition of cellular structure into sandwich panels. This work is focused on combination of these approaches. Among cellular structures, auxetics are of high importance. Auxetics are mechanical metamaterials which exhibit negative Poisson's ratio. This means that such a structure shrinks under compression in opposite to standard materials with positive Poisson's ratio. This brings enhancement of impact energy absorption because the shrinking structure enables to concentrate amount of material under penetrating object and brings in this way a better penetration protection. Such auxetic lattices also preserve the lightweight nature and possibility to use tailored properties using additive manufacturing techniques. Directions to enhance the Impact energy absorption consists in filling of the cellular structure with polymeric fillers. Together with the lattice, the filler form interpenetrating phase composite. Here you can see some results of our previous research, which was focused on interpenetrating phase composite made from open cell, metal foam, and polyurethane putty. And the lower and upper diagram show the difference between the behavior of the plain metal foam and the IPC, which exhibited strain rate sensitivity even at low impact energy induced by a drop tower. The possible polymeric fillers were tested also at higher strain rates. Here you can see three representatives of such candidates to fill the open cellular structure or the open lattice to enhance the impact energy absorption properties. Here you can see significant strain rate sensitivity exhibited by polyurethane putty. On this diagram you can see porous polyurethane foam, which will be also presented in our results here. And a strong strain rate sensitivity was observed also in ordnance gelatin, which is presented also in the further results. In this research we tested combination of three types of auxetics. Two ones are two-dimensional auxetics and one of them is three-dimensional auxetics, and these three types of auxetics were then filled by two types of filling material, ordnance gelatin and polyurethane foam, and last group was kept unfilled for reference. These samples were manufactured using selective laser sintering from authentic steel alloy, and the design of that samples was selected in order to achieve at least one unit cell inside the structure without being at the contact phase. Two types of polymeric fillers were used: low expansion polyurethane foam and ordnance gelatin. The samples were tested in quasi-static conditions and under high strain rate conditions using split Hopkinson pressure bar apparatus, which is located in Czech Technical University in Prague in laboratory of high strain rates phenomena. This Hopkinson pressure bar is equipped with 1.6 meter long incident bar and transmission bar and 0.2 meter long striker. The signal from the strain gauges is recorded by high-speed digitizer, and the loading scene is then captured by a high-speed camera with frame rate higher than 100,000 frames per second to enable further evaluation of strain at the surface of the deforming sample. The strains at the surface of the deforming sample were evaluated from the obtained images from high-speed camera using a custom digital image correlation tool based on Lucas-Canade tracking algorithm. Using this tool, a full field strain measurement were performed from array 6x6 features on surface of each sample, and from these displacements obtained by digital image correlation, then Poisson's functions were evaluated. For each sample, the dependency between the Poisson's ratio and longitudinal strain was then obtained. Now briefly to the results. From the SHPB apparatus and its instrumentation, stress-strain curves were obtained, and from the stress-strain curves the strain energy density was evaluated and plotted against the strain rate. For all the group of samples, the results show slightly positive effect of the filling material on the strain energy density. In this table, the ratio between unfilled and filled specimens in terms of increase of strain energy density is presented for all of the types of the auxetic structure, and you can see that while at static condition the increase was not that significant, and even for the ordnance gelatin a decrease of strain energy density versus mass was observed. In the dynamic condition, all of types of auxetics with both types of filling show increased strain energy absorption properties. Now to the core of the results of this investigation. While the filling exhibits a positive effect on energy absorption properties for all of auxetic materials at tested strain rates, the auxetic behavior due to the presence of non-auxetic material in the auxetic lattices is suppressed, and the presence of the filling is a trade-off between the auxeticity and the enhanced energy absorption properties. For all of types of structures, we can see that the lowest curve of the Poisson's function is observed for the unfilled samples, and then the filled samples exhibit similar shape of the Poisson's function, but the Poisson's ratio is higher. The same repeats in the three-dimensional reentrant samples and also for the missing grip samples. Now briefly to the conclusion. SHPB apparatus in Laboratory of High Strainic Phenomena and Dynamic Testing of Czech Technical University in Prague was used to evaluate influence of the polymeric fillers on auxetic behavior of additively manufactured auxetic lattice. The optical strain measurement using a custom DIC tool was successfully applied for full field strain measurement and enables the Poisson's function evaluation. The SHPB test of polymer filled auxetics confirmed the positive influence of both types of tested filling at dynamic strain rates. On the other hand, the optical measurement of the strain at the surface of the samples showed a slight suppression of the auxetic nature of the tested lattices. Thank you for your kind attention.